So in day 2 of graphing, we're going to combine what we learned last class about horizontal asymptotes or end behavior, vertical asymptotes, and potentially slant asymptotes, and combine all of that together with some other things we know just about graphing in general to graph these rational functions. Some of those things we know is about X-intercepts and Y-intercepts. Really pretty simple concept, but the way to find an X-intercept is to find any X value whose Y value is 0, because the coordinate is some number comma 0. Now Y-intercept is any Y value whose X value is 0. Basically plug in a 0, we're going to get out the Y-intercept, the coordinate 0 comma some number. So you can kind of see in these two examples what we have to do to find the X and Y-intercept. For a regular linear function, all we have to do is, for the X-intercept, is set the entire equation equal to 0 and then solve the function. This would be 7 over 4 comma 0 as the X-intercept. In the Y-intercept, all we have to do is plug in a 0 for the function for every X. So 4 times 0 is 0, 0 minus 7 is negative 7, so the Y-intercept is 0 comma negative 7. Now when we make this a rational function, it's really pretty simple. Again, to find the X-intercept, we just set the entire function equal to 0 because f of x is like y, so we're still setting y equal to 0 and solving. And really, I'm worried mostly about the numerator being equal to 0 because that's how a fraction would be equal to 0. So we can factor this one and we can solve. Zero product property tells me that x equal to 5 and 2 are my X-intercepts, so 2 comma 0 and 5 comma 0 are my X-intercepts. That would be where the graph crosses the x-axis. My Y-intercept is where we plug in the 0. So I plug in 0 for every x that was in the original equation, evaluating at 0. And we'd get out that 10 over 4, and then that's 5 halves. So my Y-intercept, there should only ever be one Y-intercept, is 0 comma 5 over 2. Now we're going to utilize that as well as the asymptotes and end behavior to graph this rational function. Okay, this one's kind of willy-nilly. We'll get there, I promise. Part A, if you notice in this question, here's f of x, and in fact they've actually factored it for us. How nice. If we're finding the end behavior, that's Bobo, Botan, or eats DC. Now this one is eats DC. So the exponents are the same. We're going to divide those coefficients. We should have a horizontal asymptote at y equal to 1. Okay, here's my horizontal asymptote at 1. Phew, drawn that. We have that on our graph. Good start. It says find any vertical asymptotes or holes. So to check for holes, remember what I'm going to do is I'm going to look and see if this graph essentially has a hole somewhere. And that is going to occur when some of these factors cross out. So x minus 3 is going to be where my hole exists. So there's going to be a hole at x equal to 3. And I'm just going to put a little arrow here, and I'm going to say hole because we need to remember that for later. Just a note to myself. And we find the vertical asymptotes by setting whatever's left of the denominator equal to 0. This would give me that 5 over 2 is a vertical asymptote, which is 2.5. So I'm going to come in at 2.5 and draw my vertical asymptote for this rational function. Pretend that's a straight line, please. Wow. For my x-intercepts or zeros, also known as roots, the places where this graph can cross the x-axis, I'm going to take the factored form of this and the reduced factored form. I'm going to set it equal to 0. The reason that I'm leaving this first factor out is because I know that that's a hole, so there's no way it can be part of my 0 since it's already crossed out. Zero product property lets me know that x equal to negative 3 is going to be a root, a 0, or an x-intercept. So we have the coordinate negative 3 comma 0. I know that this graph has that coordinate point. And last but not least, we're going to find the y-intercept, which is again just plugging in 0 for x. So this is going to be, I'm going to plug it into the reduced factored form. 2 times 0 plus 3, and 2 times 0 minus 5. 2 times 0 plus 3, that's 6. And 2 times 0, that's 0. Minus 5 is negative 5. So my y-intercept is at 0 comma negative 6/5. which as a decimal is like negative 1.2. So about right there. Okay, now we get to play connect the dots. And the only two dots I really have is the X-intercept here of -3 and the Y-intercept there. And now I gotta keep drawing, so I'm gonna come in and I can't touch that vertical asymptote. And I know that my end behavior has to get closer and closer to that value of 1. So that's 1/2 of it. And for a reason we're going to discuss later, the other part of this graph is going to start up here at positive infinity and come down again closer and closer to that horizontal asymptote. Very last thing, because I already wrote a note to myself, thanks past me for writing this note about a hole, and I'm going to zoom in here for you. If I had drawn this a little bit better, we can make a hole where this graph crosses the 3 and say that that is a gap in the graph because we have a hole at 3. Not that I drew that in the most effective way, but there it is. Now, there's a lot that you have to do to graph rational functions. So to make it slightly easier, or at least more organized for you, we've come up with this method called RATEY. RATEY stands for something, so it helps you remember what all you need before you can graph any function. So look at the warning up here. It says before you use RATEY, you must factor both the numerator and denominator and remove any common factors. These factors that you cross out tell you where the holes are. So we're always going to check for the holes first. RATEY stands for, or the R in RATEY stands for root. Also known as the X-intercept, also known as the 0 of the function, is the root. You're going to set the numerator equal to 0 and solve the function. These are the X-intercepts, and we write our answers today as coordinates, number, comma, 0. What's important about this is that we know that graphs must pass through any roots on the graph. So any of these values we find, you must cross the x-axis there. And more importantly, you cannot cross the x-axis anywhere else. Only at these values we find, and R is for root. The A stands for asymptotes, specifically the vertical ones. We're going to set the denominator equal to 0 and solve. These are full-on equations, so it should be x equal to some number, some vertical line, some Vux line. It is a boundary line, so it's going to create sections of our graph for ourselves. The graph can come close to, but it should never cross or touch that asymptote. The T is for tendency. There are two tendencies you can find. You're looking for if any factors have squared terms. So something else you can think about is T is for tendency or 2, because if you have any squared terms or any 2 terms in the top or bottom, something specific happens. You have a tangency at the root if there's a special squared term on the top, so in numerator. If there is, I don't really care what's on the denominator, but if there is some sort of squared term, that's going to indicate to you that you have tangency at that x-intercept. More importantly, and what we've been using to talk about tangency is that it's going to bounce at that x-intercept. So here, we would know that this was some sort of bounce or tangency at that 0 of 3. We've already talked about this before. It's the multiplicity of 2 bounces. You also have a second T value, or T word that we're going to check, is called togetherness about the asymptote. If there is any of those squared terms on the bottom in the denominator, I don't really care what's in the top, but if there is some sort of something down here and there's a squared, then at that particular asymptote, the graph is going to come together. Instead of being on the limits on the opposite side of the asymptote, the limits are going to be the exact same. It'll look something like this example here. Okay, so let's pretend that we have this asymptote, and instead of, like on our graph on the other side, those 2 parts of the rational function going opposite, I'm using my hands, y'all can't see me, these are going to be coming closer together or together about that asymptote. They have like the same limit on the left side and the right side. And if there is not a squared term, then around that asymptote, it's always going to be the opposite. So it's important to know that if you don't have togetherness, if you don't have a squared, they have to be opposite. So odd opposite sides of the asymptote for the limits. That will make more sense when we see a few examples, I promise you. E is for end behavior. This is your horizontal asymptotes. We're going to see how the graph is acting as x approaches negative infinity and positive infinity. And so for both of these examples here, even one that has a togetherness or one that has an opposite vertical asymptote, you see that both of them at their ends, or as they go out towards positive and negative infinity, are occurring or headed towards converging on the same value. Just to make sure you remember this, end behavior is your horizontal asymptote or your slant asymptotes, and you're only going to find a slant asymptote when it's bigger on top by 1. That's when you're going to have a slant asymptote instead of a horizontal asymptote. Bigger on top by 1. And then last but not least, the Y in RATEY stands for Y-Intercept, and just like we did on the front page, you're just going to evaluate f of 0 and write your answers as a coordinate 0, some number. Now let's hop in and use this RATEY method to see how it might help us graph these complicated functions. Alright, first things first, we need to check for holes, which means the very first thing I'm going to do is I'm going to see if anything's going to cancel out when we factor. So I'm going to take this function and I'm going to factor the top and bottom. Top does not factor to anything. The bottom is the difference of 2 squares, so I'm going to go ahead and factor that. And nope, nothing cancels out, so there are no holes in this graph. But we can find the roots. Now remember, the roots are when you set the numerator equal to 0. Quick little zero product property there, solving for x, tells me that I'm going to have a root for this function at 1, 0. Boom. There's my root. Vertical asymptotes we find by putting the denominator equal to 0. So here's my denominator, the factored version, easier to work with. I'm going to set it equal to 0, and again, zero product property in a quick little solve tells me that x equal to 2 and x equal to -2 are going to be my vertical asymptotes. And for ease, you can combine that into plus or minus 2. Now, again, that's something I can graph. So that's a vertical asymptote, a straight up and down line at -2 and 2. Boom. There's my vertical asymptotes. T is for tendency. We're going to check both the tangency, or the bounces, and the togetherness around each of the asymptotes. But notice how in this factored function, there are no squares. There's no repeated roots. There's nothing like that. So we actually have no tangency and no togetherness, which means that at both of these asymptotes, they need to meet at opposite limits. Neither of them should be going the same direction. And that at this particular X-intercept, we're not going to bounce, we're going to cross through. This is just some extra stuff. We may not write this every single time, but just while we're learning. The end behavior for this guy is bigger on bottom, which means my horizontal asymptote is going to be at 0. Now remember, this is the horizontal asymptote, and yes, asymptotes graphs should never touch, and you're like, Miss Quigley, it's freaking touching that root right there. You're right, but remember, we're talking about horizontal asymptotes for end behavior, not middle behavior, but end behavior. And then to find the y-intercept, you're going to plug 0 into the factored version of this function, which is pretty easy to do because it's all zeros. This is going to be -1 times -2 times 2, which is -1 over -4, or 1/4. So my y-intercept is 0, 1/4, which is like right there-ish. Not super accurate, but that'll do. Now there's all the information that RATEY gives me. The part that gets hard about RATEY is at this point, I can't really tell you an exact way to do this every time. What I like to do is like to look for the place that I have the most information. I have the most information, most coordinates here in the center. So let's start there. If we wanted to cross both the y-intercept and the only x-intercept I have to kind of play connect the dots like this. Which means, since I can't come back up and I can't bounce at that y-intercept, this centerpiece has to look a little something like that. Again, that's because to play connect the dots here, to connect those dots together where I don't cross the x-axis again, I have to go this direction and this direction. Can't come back down because it would cross the x-axis again. And then, because I know that this has to be the opposite limit, so this is going down to negative infinity, which means on the other side has to go up to positive infinity. And as I come down, remember I'm getting closer and closer to that horizontal asymptote. Again, this horizontal asymptote, that's a vertical asymptote, says opposite. So that means as this limit goes up to infinity, the other side of the limit should go down to negative infinity. And we get closer and closer to that end behavior. And voila, we've sketched a really good graph of this rational function using the RATEY method. Let's check example 2. Again, before we start using RATEY, we have to check and make sure there are no factors to factor out. This is going to be x squared again, and then the denominator factors, again, difference of 2 squareds, x plus 7, x minus 7, so nothing cancels, and there are no holes. We find the roots by setting the numerator equal to 0. So this is going to have a root at 0, 0. That's the origin. We find vertical asymptotes by setting the denominator equal to 0. Zero product property tells me that x equal to negative 7 and x equal to 7 are my vertical asymptotes, which is something I can graph. Here's negative 7, and here's 7. I have my vertical asymptotes. Tangency and togetherness, remember I'm looking for 2's or squareds, and I have a squared term in the numerator. That has to do with tangency, so I'm going to have a bounce at the value x equal to 0. And just for good measure, again, because we're learning, you don't have to write bounce on here if you get it, but I need the reminder every once in a while. So I'm going to write bounce at that root. For togetherness, there is no squared term in the denominator when I factor. So there is no togetherness, which means both of these horizontal asymptotes should have opposite limits. The end behavior, this is an eats DC graph. So we're going to divide those coefficients. It should be at 1. So that's a horizontal asymptote or end behavior at 1. And at this point, oh sorry, we need our y-intercept. Hopefully you notice already what the y-intercept is because it's the same as the x-intercept, but I'll show you anyways. As 0 squared, 0 plus 7 times 0 minus 7. Yeah, no matter what you do, you're going to get 0, which we already know because 0, 0 is both an x and y-intercept. Okay, now is when the crazy part happens because you don't have a lot of information to go on. So my first instinct when I think about a bounce is bouncing back up. And let's see what kind of mess I make of this graph because I need to be able to erase. If I was to think that this graph bounced like this, boop. Okay, that would mean, because these have to be opposite limits, that this side needs to go down here and then up towards the y or the end behavior. And I already see that that's a problem. Am I allowed to cross the y-axis, or sorry, that's the x-axis. Am I allowed to cross the x-axis right here? RATEY tells me that the only root is 0, 0, so I cannot pass through right here. So something is amiss, so that's why God made erasers. We're gonna erase a lot today, don't worry. Hopefully I don't erase too much. I'll write the word bounce again. So let's try something else. Let's try bouncing the other direction. So So if I go maybe something like this, again, because the vertical asymptotes must have opposite limits, we would have something that looks like this. And those two pieces on the right side and left side are getting closer to their end behavior, to y equals 1, and they don't cross the x-axis when they're not allowed to. So that looks pretty good to me. Again, there's not really any certain way I can tell you to do these problems every time because it's kind of a puzzle, which is really cool. Putting the pieces of what you know together and making sure you follow all of the rules from RATEY. In these next two examples, I've already found all of the information for RATEY. I think at this point we just need help actually graphing it. So if you're needing help finding all the RATEY stuff, maybe come in so I can help you, or go back and watch those other parts again. But in this first one, example 3, here's all the information I got from RATEY. Let's graph it. We know there are no holes, but there is a root at 1 and at -4. We also know there's a vertical asymptote at -2. Since there's a square in the denominator here, even though I wrote it out here, but those are the same, so that's squared, that means I'm going to have a togetherness at this vertical asymptote. The limit should be going to the same direction. The end behavior, or the horizontal asymptote, is at y equals 3. And the Y-intercept here is at -3. Boom. There's all my information. I just need to play connect the dots. Again, can't really tell you exactly how to start every time. I like to look where the most information is, where the most coordinates are, which for me is right here. And if I play connect the dots, I have to connect the dots this direction, which means my graph might look something like this. And since we have togetherness at this vertical asymptote, I know that that limit is the same, which makes a lot of sense because I can cross through that -4 and then make it to my end behavior. Boom, we've graphed it. The last example here, and if you need to pause and try to make sense of all of these RATEY here, make sure if you're doing that you've noticed there's this negative in front. I missed it the first time I did these problems, so make sure you maybe highlight that, circle it, star it, underline it, whatever. Nothing cancels out here, so there are no holes. The roots are -1 and 2. We can graph that. Again, that's found by setting the numerator equal to 0. We have two vertical asymptotes, one at -3 and one at 4. I have both a tangency and a togetherness. So I'm going to bounce at x equal to 2. And at the vertical asymptote of -3, I'm going to come together. And since I know that means that at the other vertical asymptote, it has to be the opposite. And at the other x-intercept, I have to cross through. Last but not least, I guess it's actually not last, my horizontal asymptote, my end behavior is y equal -1. And my y-intercept is positive 1/9. Again, positive in case you missed that negative in the very front. So here's the information I have. Again, I like to start where the most information is, and the most information here is in the center. To play connect the dots here, I have to go from the first point to the y-intercept and then bounce off the other x-intercept. So there's the center part. And based on the togetherness, based on the tendency there, I can be together at this this vertical asymptote that had the same limit. So here it is having the same limit, but then I have to curve out by that horizontal asymptote. And based on, again, the t part of RATEY, this has to be the opposite limit. So this limit on the left side goes up to positive infinity. So on the right side, we need to go down to negative infinity. And again, kind of swerve out at my end behavior at my horizontal asymptote. And voila, we've graphed the function. RATEY is so helpful for graphing these functions. Make sure you know what each of the letters stand for and how to find the roots, the vertical asymptotes, the tendency, the end behavior, and the y-intercept so that you can also graph these functions.